Good evening, ma'am. Today, we members of Group C6 are here to give a presentation on file system caching mechanism in Linux. This presentation briefly talks about file system caching in Linux, including the topics page caching, write-back policies, tuning write-back policies, kernel mechanisms, and real-world impact of Linux file system caching. Now, before we dive right into file system caching, let's understand what it actually means. So it is basically a technique by operating systems to improve file access performance by storing the recently accessed files from the disk in page cache or in RAM or the recently accessed data into fast storage locations. Now, to perform this, it uses page cache. Page cache is basically a memory location inside RAM which stores file data of the files which were recently accessed from the disk. Then we must familiarize ourselves with the term called dirty page. This basically means the page whose data has been modified, but it's not written back to the disk. Now, the process of writing these dirty pages back to the disk is called as write back. And then the time when these data is written back to the disk are decided by write back policies, which we'll be looking forward. But right now, let's dive into how page cache works. First, let's talk about read from disk. In page, let's assume that we have page cache memory, which is currently empty, and we have a user program which is requesting for files. Since there's nothing available in the RAM currently, the file requested from the user program would be directly taken from the disk or directly read from the disk. And this file data is stored in page cache for future use, and also the result of these read and pread system calls is sent to the user program. Now, when the user program again requests for a new data file, the kernel first checks if the data is already present in the page cache. If it is present, we call it a cache hit. And the data is immediately returned to the user program from the page cache. If the data is not present in the page cache, then we call it a cache miss, which means we'll have to go to the disk, read the data from the disks. We store that data into page cache for future use, and we also return the data back to the user program. Now, writing these modified data files into disk is not a direct process. In fact, these changed file data of particular files are first stored in page cache under the heading of dirty pages. Now, using write-back policies, it is decided when to send these data back to the disk. Now, these write-back policies have two triggers, which includes threshold-based and time-based. I'll talk about these in details in this current slide. So first, threshold-based flush. This means, as the name suggests, there is a particular threshold in the memory fixed by default, for example, 20%, where if the dirty page value or size, memory size exceeds the threshold value, then those dirty pages memory or those dirty pages are flushed back to the disk. For example, if the default value of the threshold-based flush in our current Linux system is 20%, and let's say we have 8 GB memory, which means if the dirty page memory exceeds the value of 1.6 GB, then the memory or the dirty pages are flushed back to the disk immediately. Then we talk about background flush. Background flush basically suggests that if the flushing of if we have a certain background payments of a fixed threshold value, that is maybe 20% or 10%, which is basically lower than the threshold flush value. If that is exceeded or crossed, then the dirty pages are flushed back again to the disk. Now, the difference between the threshold and background flushes, background flush has a lower threshold value as compared to the threshold-based flush. For example, background flush will have 10% as a threshold value, whereas the threshold-based flush would have 20% as its threshold-based value. Then we have expiration-based flush. These, as the name suggests, again, they have a particular default time limit value. If the time limit is exceeded, then the dirty pages are flushed back to the memory or flushed back to the secondary memory. And this is done by the command vmdirty expire sentiments. Then we have periodic flush. By default, these values are set to 5 seconds, which means every 5 seconds, the page cache is checked for dirty pages. If there are any dirty pages, they are flushed back to the disk. Then we have manual flush. Basically, they are manual triggers made by the admin to flush all the dirty pages back to the disk. Talking about the process of these write-back decision process. So when the dirty page in the cache is encountered, we check the following conditions. If the threshold value of our background flush or threshold flush is exceeded, then the dirty page is written back or flushed back to the main memory, to the secondary memory. Else, if the threshold value is not exceeded, we check the expiry time. If the default expiry time is not exceeded of the dirty page, then we move on to the manual sync, or where the admin themselves uh, trigger the flush mechanism to flush the data or the dirty pages back to the memory. Now, tuning these write back policies and behavior would be further discussed by Reshma.
Reshma from S4CSEC. I am going to cover the topic of tuning write-back behavior in the Linux. It is used to check the balance between performance and data safety. Write-back catching temporarily. Let's know what is write-back. Write-back catching temporarily stores modified data in the memory known that as dirty pages. This improves performance, but there is a high risk of data loss. If the system crashes, we might lose the data. This graph shows how it affects the behavior based on data page. We have VM dirty ratio to check this. The blue bars indicate the dirty pages and the purple bars indicate how much data is being flushed. Few parameters to check this efficiency. Parameters like VM dirty ratio and VM dirty background ratio, and system administration will help us to know the performance and the safety graph. Now let's talk about tuning trade-off data. Based on the VM dirty ratio, we can know the performance and the data safety and usage. If the VM ratio is 10%, the system will be very slow and the data will be very safe. And it is much used for critical services like databases. If the VM ratio is 20%, there is a balance between data safety and the performance, and it is used for general purposes. When it's 30, there is a further increase in the performance, but it is a higher risk. This is for mainly developers and all. When it's 40 to 50, there is a massive speed, but there is no safety in the data. It's not used for normal purposes. So better we use it unless it's necessary. Let's talk about write through versus write back. To understand write back better, let's quickly compare with write through. Before that, let's know what is write through. Write through is basically it writes directly to the disk. It's a safe one, but slow because it system has to wait until each write is finished. In the write back, it actually writes directly to the memory cache. Then the system flushes to the hard disk. This is faster, but there is a high risk of data loss if the system is not restoring before crashing or before shutting it down. This is why tuning write-back parameters are important. It will make us know how much speed and how much safer the data should be. Let's talk about monitoring tools. This helps us to check the performance of the system. There are three main common tools: free, VMSAT, and IOSET. Let's talk about free first. Free shows how much memory is used. Even it also includes the cache memory. VMSAT, it gives detailed system stats, including paging, memory activity, and I/O. Let's talk about IOSAT. The memory disk's performance, I/O performance, it monitors the I/O performance and helps us to understand caching efficiency. By regularly checking, we can make sure the write back is not causing any problem or any risk of losing the data. In summary, let's conclude everything. Write back caching in Linux can greatly improve the speed and the data efficiency. Using this tuning parameters, it is more safer and there is high performance. Now I'd like to invite NEEMA to continue the SINGH overview.
My name is NEEMA from CSC batch. So let's explore how Linux handles writing data from memory to disk and why it matters for both performance and data safety. So we will begin with a tool that plays a key role in ensuring our data is actually saved. That is the sync off command. So to protect the data, Linux gives us a simple tool called sync off. This command tells the system to flush all the data pages to disk immediately. This ensures that all your modified data is not just in a memory, but actually returned to a disk. And it's often used before shutting down a system, during testing, and after important operations like saving a database. So it's a safety button actually, just like pressing save manually. And we have given example usage. From there you can see like these are the codes we are manually using to clear caches. Just like the clearing page caches, clears VINOD and entry cache, and as well as clears all the caches. So these are the useful for these are the useful codes for freeing memory, especially during debugging or testing. So here are some important kernel components. First one is background daemons. These run silently and handle memory operations without needing the user's help. Flash daemons. They take care of writing data pages from memory to disk and also ensures that your data is safe and system stability is maintained. And the last one is K-worker threads. These are the general purpose threads that handle various background tasks like managing I/O operations and boosting file system performance. So even if users don't run sync, the kernel handles everything smoothly, writing back the data as needed. Together, these mechanisms make sure that system is fast, safe, and smart, even when we don't notice it. Write back caching to improve the performance. Instead of writing data immediately to disk, it stores it in a memory first. The system uses smart thresholds and timers to decide when to write the data to disk. This helps balance speed and system level. The good part is that we can tune this behavior using parameters like vm.dirty ratio and dirty x86 to make it match our system needs. For our important systems like databases or servers, tuning becomes very important to avoid data loss and improve the efficiency. So here's a simple flow chart. So this flow shows what happens in a Linux system when we save or modify the data. So first, when a program writes the data, it doesn't go directly to the hard disk. It's written to memory first, which is much faster. Then that data is temporarily stored in the page cache, a part of RAM. This helps the system respond quickly without waiting for a slow disk operations. So here, the Linux wait before writing the data to disk. This delay is intentional and helps group multiple writes together to improve the performance. But during this wait, the data is in the form of data pages. It's not yet saved permanently. So after a certain time, or if a memory gets full, Linux decides to flush these data pages, means it prepares to write them to disk. So finally, the data is returned to the hard drive or SSD, making it permanent. So this whole process balances speed and safety. And it's fast because of caching and safe because the Linux eventually flushes it to the disk. Now let's understand how this affects real life systems. So write-back caching definitely makes things faster. Like apps don't wait for every disk write, so they respond quickly. But here's the risk. If the system crashes before those changes are returned to disk, you will lose whole data. So that's why the critical applications like databases use special function called fsync to immediately save the important changes. So we must tune it depending on whether speed or safety is more important. So it's just like editing a Word file. Like if you don't hit the save, the power goes out, you will lose everything. So that's why the data pages are called the unsaved changes in the memory. So to conclude, Linux write-back policy is all about balancing performance with safety. It gives us the speed we need, but also the control to protect our data. Whether it's through kernel mechanisms, manual commands like sync-off, or tuning parameters like VM.data ratio, we can decide how and when our data is returned to disk. So understanding these concepts isn't just a technical knowledge, but it's a key to build reliable, efficient system. Thank you.